and this is fourth method. The fourth method is decreasing growth rate method, right? What is the fourth method? Decreasing growth rate method. The formula for decreasing growth rate method is Pn is equal to P naught into 1 plus R naught minus D bar divided by 100, and the second term is 1 plus R naught minus 2 D bar divided by 100 up to nth term, n times of D bar divided by 100. Let's see the example problem. As usual, let's take year on the first column and population on second column. In 1960, the population is 5,55,000. Sorry, 55,500. 1970, 63,000. Let me write it properly. 63,700. In 1980, the population is 71,300. 1990, 79,500. Okay, this is the population, and I want population for 2020. I want population in 2020. What you have to do? First, you have to find the terms present in the formula, right? So first you have to find P naught. You already know. This is latest known population, and it will be P naught. And then you have to find percentage increase in population. Then only you will get latest percentage increase in population, right? So percentage increase in population. How do you do that? The difference of these two, 63,500, let me write it here, 63,700 minus 55,500 divided by 55,500 into 100. This is the percentage increase, right? So upon solving, you are going to get 14.77%. So 14.77%. Similarly, between these two decades, you are going to get 11.93%. How do you do that? Percentage increase is equal to 71,300 minus 63,700 divided by 63,700 into 100. You are going to get 11.93%. Similarly, between these two decades, you are going to get 11.5%. So what is the R naught value here? R naught is this one, latest percentage increase in population. These are also percentage increase in populations, but this is the latest percentage increase in population. So R naught is this one. And then you have to find the D bar. What is the D bar? Decrease in percentage increase. See the population trend here. Between first two decades, the percentage increase is 14.77%. But during the 2 and 3 decades, percentage increase is only 11.93%. It means the percentage increase is decreased. That decrease in percentage increase you have to write in this fourth column. So decrease in percentage of increase in population is 14.77 percentage minus 11.93 percentage. You're going to get 2.84. 2.84. Similarly, between these two, the percentage decrease is 11.93 minus 11.5. The percentage decrease is very small, 0.43. These are the decrease in percentage increases. But you have to find the D bar. D bar is equal to average of these two. 2.84 plus 0.43 divided by 2. You are going to get d bar as 1.635. This is the another term. So you know the P naught value, you know the R naught value, and you know the D bar value. If you know all three values, you can directly find the future population using the previous formula I have written. So P naught is equal to, let me show it here so that you will understand. Yes, Pn is equal to P naught. What is the P naught value? 79,500 into 1 plus, what is the R naught value? 11.5 minus D bar 1.635 divided by 100 into, this is the first term, and then R naught minus 2 into 1 point, D bar is 1.635 divided by 100. This is the second term. How many terms we have to write? We have to write 3 terms, because between 1990 and 2020 you will have 3 decades. So you have to write third term, 1 plus R naught minus, sorry, R naught means 11.5%, right? 11.5 percentage minus. Similarly here also 11.5 percentage minus 3 times of 1.635 divided by 100. Upon solving this equation, you are going to get population 2020. Population in 2020 is equal to, approximately you are going to get 1,765. This is how you are going to calculate the future population using decreasing growth rate method. Okay, and about fifth method and sixth method, you don't need to bother about them. They are the theoretical ones, graphical and simple graphical and comparative graphical methods. You don't have any problems on that. So why we are studying all these population forecasting techniques? Because if you want to design a system, first we have to fix the discharge value. As I told in the previous lecture, the discharge is depending on population, I mean future population, water demand, and design period. These are the 3 factors on which our discharge is depending. We already studied population, how to find the future population. Now let's see water demand. Water demand is always constant. It is not like population, it doesn't vary. So water demand is generally, for domestic purpose, the water we need to supply per person is 135 LPCD, 130 liters per capita per day. Liters per capita per day. Okay, LPCD. Generally, water demand will depend on many factors, right? Depending on the standard of living, depending on standard of living, cost of water, and then whether the type of water supply means whether it is continuous supply or intermittent supply. Intermittent supply means in a day you might supply water for 1 hour or 2 hours, like that. In continuous supply, water will be provided 24/7. Similarly, whether the water tap connection is metered or not. Metered connection. Next, quality of water. Quality of water will also affect the water demand. If you have very good quality of water, then water demand will be more. If the quality is less, you're going to use less water, etc. etc. You will have few other factors that could affect the water demand. Okay, right. How to find the water demand? What is how to find the water demand value exactly? For to find out the water demand, what you do is water demand is represented in LPCT. You will take a city or town. You will find the average annual water consumption. Average annual water consumption. This is the amount of water consumed by the community in 1 year. The whole community is going to consume some X amount of water in 1 year. That is called as average annual water consumption. If you want to find the water demand per person, you have to divide it with population. Since I have told you per capita, LPCD means liter per capita. Per capita means per person. Population into 365. Why 365? This is annual data, but I want LPCD in terms of days. That's why divide it with 365. Okay, this is the average water demand by one person. But you cannot depend purely exclusively on this one value. Generally, the water demand will vary depending on the season, depending on the day, depending on the month, and depending on the hour also. So, if you see maximum seasonal consumption, maximum seasonal consumption will be greater than average value. Obviously, during the winter season you will use small amount of water. During the summer season you are going to use more amount of water. So maximum seasonal consumption will be equal to 1.3 times of the average annual water consumption, right? Definitely it will be 30% more than average value, average consumption value. Similarly, if you see one particular month among in the summer, during May month you will use, definitely you will use more amount of water compared to other months. So to accommodate such things, generally you will find maximum monthly consumption. Maximum monthly consumption will be 40% more than average annual water consumption. Similarly, the maximum daily consumption or maximum daily demand, it will be equal to 1.8 times of the average annual consumption. On one particular day, the temperatures might be highest. On such day, you are going to use 80% more than average value. Similarly, during that maximum day, on particular hour, you might be using more amount of water. That is called as maximum hourly demand or maximum hourly consumption, and it will be equal to 1.5 times of the maximum daily demand. So it can be written as 1.5 into, how to write maximum daily demand or maximum daily consumption? It is nothing but 1.8 times of the average annual consumption. So you're going to get 1.5 into 1.8, 2.7 times of the average annual water consumption. These are the variations in water demand. These are the variations in water demand. Why it is varying? Depending on the season, depending on the month, day or hour, the consumption or the water demand will be varying. You should not always exclusively depending on the average value. You should also consider these things while designing our components in water supply system, right? Now let's see how to calculate the total water demand by each person in the community. As I told you, for domestic purpose, the water consumption, the water required by one person is 135 LPCT. But in addition to this, definitely the community or the city will have industries. You have to supply water to the industries also. For industries, you are going to supply 50 LPCD. For institutions or commercial business, for such things you have to provide 20 LPCD. Similarly, for public use like public toilets or gardens, public gardens, parks, like that, you are going to supply 10 LPCD. In addition to this, you have to satisfy the demands of fire. You have to supply water for the fire demand. To extinguish the fires, you have to supply water. The fire demand is generally for Indian cases, it is 1 LPCD, but we have different formula. We have different formula to calculate fire demand, and totally we have 4 formula for that. They are Kuchling formula, they are Kuchling formula, Freeman formula, Buston formula, National Board of Fire Underwriters formula. These are the 4 formula you have to remember. Let me write them for you. You have to remember those formulae because they are very important. At the same time, it is also a little bit easy to remember. I will show you why it is easy. All the units in, let me write it first. What is the first formula that I told you? Kuchling's formula. Kuchling's formula is given by Q is equal to 3182 root P. Where, let me write all the formula first. Second one is Freeman formula. Freeman's formula. In this formula, the discharge will be given by, discharge means fire, here Q means fire demand. Freeman's formula is 1136 into P by 5 plus 2, and the third formula is National Board of Fire Underwriters formula, and it is given by Q is equal to 4637 root P into 1 minus 0.01 P. Okay, 0.01 root P. And the last one is Buston's formula. And the last one is Buston's formula. And the Buston's formula is given by 5663 root P. 5663, the Q value is given by 5663 root P. In the all 4 formula, Q is equal to fire demand in terms of liter per minute. The units for Q here is liter per minute. All these 4 formula are empirical formula. So when the empirical formula comes, you have to remember the units. You cannot substitute the values on your own units. You have to substitute the units in the given format, liters per minute. Similarly, P is equal to population in thousands. Population in terms of thousands. It means suppose the population of city is 25,000. Okay, the population of a city is 25,000. Then the p-value will become 25. The p-value will become 25 only in case of this fire demand formula. Don't assume that it is applicable for all the formula. This formula is applicable only for these four methods. While substituting p-value in these four methods, we have to substitute the value in terms of thousands. If it is 25,000, you have to substitute it as 25, right? Okay. This is the fire demand. And then let me write. So fire demand, you have to, if you want to find the total demand, you have to all these values: domestic, industrial, institutional, fire demand. In addition to this, you will have some extra provision. You have to supply some extra water, nearly about 15 to 20%, for compensating losses and thefts. Definitely our supply system will have some leakages. At the same time, few people might be thefting the water. To compensate those things, you have to supply 15 to 20%, nothing but generally 55 liters. Okay, after adding all those demands: domestic demand, industrial, institutional, fire demand, public use, and the losses, you are going to get total demand. The total demand of water will be ranging from 270 to 335 LPCD. This is the amount of water per person you have to supply in a city. Okay, in case of mega cities, I mean in case of metros with proper sewerage system, in case of metros with sewerage system, you have to assume that the domestic water demand is 150 LPCD. Generally the domestic water supply is 135 LPCD, but when you, in case of metros with sewerage system, definitely the water consumption will be higher. That's why they have taken it as 150 LPCD as per CP. Okay, CPHWO something, right? Central Public Health something. I didn't remember the abbreviation. Okay, they have given for metro cases you have to take it as 150 LPCD, right? Next, if you complete this, we will go for the third factor. What are the all the factors that are affecting the discharge? Q value, population, water demand, and design period, right? We studied population, we studied water demand. Now we'll see design period. Okay, right. The design period will be taking based on the probability of failure. Probability of failure. If you take time on x-axis and probability of failure on y-axis, probability of failure of system. Suppose if you draw a graph between these two, you're going to get the graph like this. If the design period of your system is very small, In such cases, the probability of failure is very high. Similarly, if the design period is very high, you are taking the design period as very high, then the probability of failure is very high. So if you want to design a system, you have to design it uh, in such a way that the probability of failure is minimum. So you have to take the design period of the system between these two values or in this range. This is the design period you have to consider. You should not take very small, at the same time you should not take very high. You should take in between these two, so that the probability of failure is minimum. Okay, right. This is flat line. Don't I was not able to write properly, but this is a flat line parallel to x-axis. Okay, right. So let's see the design period for different components in the water supply system. In case of pumps, the pumps we are using in the water supply system, the design period should be 15 years. Remember them, very important. And wherever there is a pipe, for pipes the design period is 30 years. Where do you see pipes? Distribution mains or distribution system. If you write it as distribution system, it will cover all the things. For distribution system, it is 30 years. Treatment units. For treatment units, the design period is 15 years. And storage dams. For storage dams, the design period is 50 years. These are very important, very important. People ask for state examinations. These are the design periods. Similarly, whenever you want to design the pumps or filters like that, you have to design for 1.5 times of the average daily demand. You should be able to pump 1.5 times of the average daily demand water. Similarly, the distribution mains should be designed for total draft. This is very important. Total draft. The meaning of total draft or coincidental draft. Total draft or coincidental draft is equal to fire demand plus maximum daily demand or maximum hourly demand. Maximum of these two. Let's say this is 300 LPCD, the sum of these two, and maximum hourly demand is 320 LPCD. Then the total draft will be 320. Or if it is 350 and this is 300, then total draft or coincidental draft is 350. Okay, you have to take maximum of these values. This is very important definition. Total draft is maximum of either sum of fire demand plus maximum daily demand or maximum hourly demand. You have to take the highest value between these two. Okay, this is called total draft. So distribution main should be designed for total draft. Okay, right. If you know these things, that is sufficient to design the Q, total discharge value. Population, water demand, and design period. These are the things you have to remember. Okay, we'll stop here. Thank you.